In this video, I just want to give a brief introduction to something called the graph miners project. So we learned about graph miners in the last video, and I mentioned on the course website that miners play a really important role in graph theory. Well, the graph miners project is sort of what thrust them into the limelight, if you will. So this project essentially proved one major result, which is what this video is going to talk about, but of course along the way they proved a lot of other really important results. And in particular, they used a few proof techniques that ended up being really important and applicable to a lot of graph theory. But the project itself was started in the 80s by Neil Robertson and Paul Seymour and lasted for just over 20 years. And the proof of the result that we're about to talk about takes over 500 published pages and more than 20 papers. So this is a huge result, and so we're just going to try and condense the essence of it into this short video just to give you an idea of what it's about. So before we do that, I want to talk about a well-quasi-ordering. So this definition is going to be very similar to the one about equivalence relations that we saw several videos back. So a well-quasi-ordering is a relation R on a set X such that so two of our requirements for equivalence relations still hold. That is reflexive and transitive. So X is always related to itself, and if you have X is related to Y and Y is related to Z, then that means that X is related to Z. Okay, so those two properties, reflexive and transitive, still hold. But instead of it being symmetric, which was the case for an equivalence relation, now we're going to have this new weird condition. So for any infinite sequence in X, so here we've just got a bunch of stuff in our set, and it's an infinite set. Any infinite sequence has a pair xi, xj, where xi comes before xj, such that these two things are related. Okay, so xi is related to xj. Another way to sort of think about this, there are sort of two conditions, but the one that we usually think about is it's not allowed to have something called an infinite antichain. So no infinite antichains, which basically means that your set X is not allowed to have an infinite subset where nothing is related to anything else. Okay, because if it does, then it's not well quasi-ordered, it would just be quasi-ordered. Okay, so this idea of every time you have an infinite sequence, things are related, that's going to come up in this result. Okay, so let me just state the result in sort of plain English. So this theorem is Robertson and Seymour's result, sometimes called the Robertson and Seymour theorem. And it says that in any infinite set of graphs, there are two graphs such that one's a minor of the other. Okay, now that seems relatively straightforward to state, and I can promise you that the proof is far from straightforward. So said differently, why did we learn about well-quasi-orderings? You could also say this using the following language. The set of all graphs is well-quasi-ordered under the minor relation. Okay, so coming back up to well-quasi-ordering, if we want to think about our set X being all graphs, every single graph ever, right? Any kind of combination you can make with vertices and edges. And now our relation is going to be the minor relation. Okay, so a graph is always a minor of itself. We saw that in the last video, right? It's not a proper minor, but it is a minor. And then if you have that Y is a minor of X and Z is a minor of Y, then of course Z is a minor of X. Right, so this transitive property still holds. Or said in the opposite direction, if X is a minor of Y and Y is a minor of Z, then X is a minor of Z. Right, and we saw that in that chain of minors we made in the last video as well. Okay, and then this is the sort of surprising part. If you have any infinite set of graphs, there's always going to be two graphs in there such that one's a minor of another. Okay, now, it may be sort of hard to sort of grasp that is actually truly something significant. So just to sort of help us illustrate, we do have one other relation, one containment relation for graphs that we've talked about this semester, and that is subgraphs. So is this true for subgraphs? And I'll go ahead and tell you that it's not true. So you might want to pause the video if you want and think for a second about how can you get an infinite set of graphs where no two graphs Like, you don't ever have a pair where one is a subgraph of another. So if you want to pause, you can. So just as one example, and there are a lot of them, you might consider just cycles. So the answer here is no. The set of all cycles is one counterexample. Okay, so think about, like, you've got a loop, right? A 1 cycle, and then you've got a 2 cycle, and then a 3 cycle, a 4 cycle, and so on. And remember, how do you get a subgraph of a graph? You're allowed to delete vertices and delete edges, and that's it. Well, as soon as you delete either a vertex or an edge in any of these, right, so this is just going to keep going on infinitely. As soon as you delete a vertex or an edge in any of these, you sort of break the cycle, and there's no way to repair it, right? So like, if, for example, I deleted this edge, well, now this thing is just a path, right? And there's no way for me to sort of like match these back up and sort of close the cycle back up. So as soon as you delete anything, right, and similarly, if I delete a vertex, the same thing happens, right? And there's no way to sort of close this back up. So as soon as you delete anything, you're going to destroy this sort of cycle property, this fact that you can, close the loop up, close the cycle up. So none of these, so here you have an infinite set, right? You could go up to C 1 billion and higher, and this will be an infinite set of graphs, and no two are a subgraph of each other. Okay, so this is a relatively straightforward example, and like I said, there are a lot of them, but it's not true that you can create, so here's one set of graphs where subgraph, right, you can see that there's an infinite anti-chain of subgraphs. This represents an infinite anti-chain, right? It's an infinite set where no two are related to each other, where here the relation is being a subgraph. And it turns out that that's impossible to do for minors. If you have any infinite set of graphs, there will always be two that are minors of each other. And that is sort of surprising, and it's a really deep mathematical theorem. So if you'd like to look it up, there's a lot of information about it online. We don't have time to sort of delve into it too deeply because, like I said, the proof is 500 pages long, and they prove a lot of really interesting results along the way. But this example should just give you a taste of the fact that it's not necessarily true, like in general. If it's not true for subgraphs, but it is true for minors, right? Then there's something that's happening here, and you can imagine, right, that all of these are minors of each other, right? How would I get C4 as a minor of C5? Right? I could just contract E. So for example, if I take this and consider contracting E, when I contract E, what's going to happen? These two, so remember, I can sort of keep all these vertices that have nothing to do with E the same, and then I'll just choose this as my representative for these two, and I'm going to slowly shrink this one into this. So this edge will stay, and then this edge that used to go up to this top vertex is now going to go to this one, right? And I get C4. So here's C5, here's C4. So of course, these are all minors of each other. C4 is a minor of C5, C3 is a minor of C4, C2 is a minor of C3, and so on. And it turns out that for any infinite set, you have to have two that are minors. So that's a very brief introduction to the Graph Minors project, and this result is the one that they prove, right? Any infinite set of graphs, there are always two, such that one's a minor of another.